equations, which means that we're going to discuss how to interpret, or how people interpret, equations of the following form. So we have a stochastic process here, x, and a sort of differential equation of this sort of form. Where x being a continuous time stochastic process is supposed to be a solution to this equation. People mean by this is that this is the same, or this means is shorthand for an integral equation of the following form. Dan, would you mind maybe muting or someone? There's a bit of background noise coming through. Yeah, thanks. Thanks. Okay. So what this means is our first task is to understand what it means to integrate one stochastic process with respect to another. So here, B of t is Brownian motion. And well, this is just a normal integral, so that should be fine. But this one here is an integral of a stochastic process expressed in terms of x here, and the stochastic process of Brownian motion. So our goal is to understand what it means to integrate one stochastic process with respect to another. So we want to define the integral where x and y are stochastic processes. After we've done that and discussed different ways of doing this and how to make sense of this, we'll go on and talk about why or how people justify interpreting this as the integral version of the equation. Now, before we do that, we'll just briefly review, briefly remember that there's three different concepts of integration. So I've linked an article by Terence Tao in the bibliography, which I think is at least worth reading the first page of. So for a real valued function, all of these are more or less the same, but they are defined distinctly, and they diverge for both higher dimensional versions of functions, and also only one of them really is going to make sense for the stochastic version of integration. So we have anti-differentiation. So for f, the integral of f satisfies the equation like so. So it's a right inverse to differentiation. We have measure theoretic intervals. So I'm going to write this like so. And this is for finding things like this is the area under the curve, under the graph of f. And this is for finding things like area, volume, mass from a density function, things like that. And then lastly, we have path integrals and their generalizations in high dimensions. So for f, we might write this like so. Should be fine. So this is, I guess, the sort of usual integral. And these are used to compute things like the work done by a particle or by a field on a particle. So in the study of non-stochastic differential equations, we usually consider integrals of the first kind. So, for example, if you have a separable ODE, you can just do anti-differentiation in order to find the set of solutions for it. However, for stochastic differential equations, the right generalization seems to me to be the integrals of the third kind. So let's just quickly remember what those mean, at least in the simple case. So we're going to be thinking about the path integral from a to b of f of x. Let p be a continuous path from a to b, and x1, I guess, yeah, x0 starting at a, x1, x2, all the way up to xn, ending at b, points along the path. Now, we do not require that xi be less than xi plus 1. So what this means is path can backtrack over itself. And can leave the interval from a to b. And what we think about the limit of the following sum where the limit is taken as the jump sizes between points on the path go to 0 for all k. And for paths in R, it turns out that these things, the value of this limit only depends on the endpoints of the path, and of course on the function on the f. And so what we do is we do it so, just identifying the path by its endpoints. But it's worth pointing out that that's not the case when generalized to sort of higher dimensions and things like that. The reason I think this is one of the sort of the right generalization of stochastic integration is because if your path, now we're integrating a possibly stochastic function f over a stochastic path, and that's sort of useful to keep in mind when we write down these definitions. The other sort of related, but I guess separate but still related thing is to keep in mind is the Riemann. I just realized I've never read this name out loud. Riemann. I'll write it down.
Stiltsches.
Yeah. Thanks. Is the Riemann Stiltsche? Make sure I can spell it right too. Integral of functions f with respect to g. For a path A x0, and now we do require that everything is all nice. Xn equal B with fixed step size we can consider this integral, the integral of f with respect to g, like so, and denote it like so. Okay. G of x k plus 1 minus g of x k. Okay. And this always exists given some conditions on f and g which constrain how wildly they fluctuate. So, for example, it exists if f and g are both smooth, but actually it exists under much more mild conditions as well. Cool. With these two ideas in mind, let's move on to discuss some examples of where stochastic integrals arise, I guess, naturally or appear as a quantity you might otherwise be interested in, and then we'll move on to the definition. Before I do so, is there any quick questions or comments? Okay, let's move on to the next set of boards. And let's talk about a discrete time example. Okay, so there's a reference in the notes to where I got this example from, and it has a lot more about the details specific to this example if you're interested. So we're going to consider a discrete time stochastic process, x, real valued, and representing the price of some asset. So you can think about x like the price, the changing price of a stock on the stock market, changing over time. For simplicity, suppose at time n equals 0, we have that x0 is equal to 0, which basically means that xn is the change in price from time 0. If we were to buy by 1 unit at time n equals 0, and sell at time n, xn would be our profit or our loss. So this process can be negative. Okay. So what we're going to do is, suppose we have a trading strategy. So by this I mean we have some strategy for buying and selling this asset over time, presumably to make a profit, and we can represent this with a stochastic process C. So Cn is the amount we own at time n, right? So if we own 1 unit at time 3, then C3 is 1, right? And C can be 0, not lower than 0, obviously, but 0 or higher. Now the change in our position. So this by this I mean the amount of money that we will gain or lose from time n-1 to n is going to be our stake, or the amount we own, times the change in price. So xn minus 1. Okay, now let's jump over to that next board. And this means our net position at time n, right? So how much we've gained or lost up to time n by following our strategy the whole time is given as follows. So yn is going to be this. I'm introducing some notation here. Which is defined to be this sum basically just summing up all our profits and losses over every time interval. Okay. And this thing here is the discrete analog of the stochastic Ito integral. Okay. Any quick questions about that?
Sorry, what's the Ito integral?
I haven't defined it yet, okay. But it's so there's different versions of stochastic integration, and the Ito integral is one version of that, and this is the discrete time version of this integral. But we'll get to that in just a moment. Yep.
So here's CK. Is there any constraint on CK or?
Yes. Yeah. So if we want, this is a good chance to go into an extended footnote I have in my notes. So let's do that. So yes, I mean, for this to be well defined, there are no constraints on C. You can just write down this sum and it's going to exist. But for it to be a physically plausible trading strategy, Cn cannot depend on xm for any m greater than n, right? Because this would mean that our trading strategy depended on stuff that happens in the future. In other words, we can see into the future. Now, to formalize this, we could think about a sequence of sigma algebras. This is called a filtration. And here, Fn represents the info at time, the information revealed by time n. So, for example, if the price was the only information we had available to us, we could define Fn to be this thing. No, this should be x0. This is unclear. Hang on. Okay, and then the way we express this idea that Cn can't depend on the future is that Cn must be Fn measurable. By the way, this is true if and only if Cn is a function of, in the case of this minimal sigma algebra here, is true if and only if there's a measurable function f such that we can write Cn as a function of the x information. Okay. So in the discrete time case, all this does is mean that we only consider physically plausible trading strategies. But in the continuous time case, it actually is a necessary condition for the integral to exist. So yeah, it's a point maybe that was worth discussing. Thanks.
Another thing is we have some constraint on how much total wealth you have to buy this. Is that reflecting C? Like, that's the amount you hope, right?
Yes, yeah. So I guess there's no constraint here, but if you were like modeling this properly, you couldn't allow yourself to take a strategy that you weren't able to follow. In the book that I reference here, that this example comes from, so X is a martingale. So the price changing represents a fair game. So that would I guess mean that it's like a zero sum sort of thing, and you shouldn't be able to expect to win in the long term. But none of these conditions. I guess the martingale condition is sort of, we can talk about that when we talk about the conditions for the Ito integral to exist. Something like a martingale condition, but much more general, is needed on X and C. Cool. Any other questions? Cool. All right, let's talk briefly about the continuous time analog of this. So suppose now that we have the price of the asset varying in continuous time, so varying continuously in time, rather. And so does our trading strategy. So we can continuously vary how much we own of this asset. And again, we'll represent our net position by y of t. Now, we might hope to estimate y of t by computing discrete integrals. By this I mean we discretize the interval up to t and compute discrete stochastic integrals. And also, if we're estimating this in a meaningful way, that finer discretizations should produce increasingly good approximations of our net position. So to express this more formally, we would hope that y of t would be the limit as n goes to infinity of the following sequence of discrete integrals. Where here tk is just one of our discrete points in this integral. And this thing is by definition the continuous time Ito integral of C with respect to the stochastic process S. Cool. So we've seen it written down. We'll go on and talk about when this limit, or some conditions that mean this limit exists, and also that pointing out that it's not exactly, or there's other options for how you might go about defining this. But before we do that, let's talk about another example of stochastic integration using sampling. Unless there's any quick questions before we do that. Cool. Okay, let's talk about sampling briefly. So we're going to recall the Metropolis Hastings sampler for Markov chain Monte Carlo sampling. So I'll write down the algorithm. We can talk about what it does. So we'll set our current state to be some initial value, and then we're going to loop, I guess, infinitely. And at each step, we draw a proposal from, in this case, I'm just going to say from a normal distribution centered at x with some fixed parameter sigma squared. And then we're going to set alpha to be the minimum of 1 and I should say we're sampling from a distribution QX. So we're going to set alpha to be this minimum, and then with probability alpha, we will output x prime and set our current state to be our newly generated state. So usually this is phrased in proposal, acceptance. Okay, so again, I won't go into too much details. It's worth pointing out that this kind of makes sense because often we might have a distribution we want to sample from where we know how to compute it up to a fixed multiplicative constant, and so we can easily compute this quantity here, and you can. I won't go into why this is going to sample from this distribution. What I'm going to do is talk about it in terms of it being a stochastic, being represented by a stochastic integral equation. So we'll let B of t be Brownian motion. So standard Brownian motion, and consider discrete time intervals tau 1. We need infinitely many of these. Tau 1, tau 2, tau 3, etc. Now, it's a property of Brownian motion that B of tau n plus 1 minus B of tau n is normally distributed. Oh, I need to define something, sorry. And we're going to define sigma squared to be the difference between any of these two time intervals. So we want the same difference between all of these time intervals. Now, it's a property of Brownian motion that the Brownian motion at time tau n plus 1 minus Brownian motion at time tau, that thing is normally distributed with mean 0 and variance sigma squared. So sigma squared being the difference in times, and that this is independent of any other increment. So no matter what, if we put another two different, or if we use a different tau here, then this will be independent from this one. Okay, so independent increments is usually how people phrase that. Have I run out of space on this board? Let's just go back to. Let's just go all the way back to the start, I suppose. Okay, and we're going to let xn be the position of the sampler at time n. So let's say what I mean by this. So I mean that every time we draw the current state x in that algorithm we had before is the current position of the sampler. And then if the sampler rejects a proposal, then we can consider the sampler to stay still at that particular time. Okay, and then it only moves on to the next state once it accepts a proposal. So to be more precise, we have x0 equal capital X0 equal to x0, our initial state, and then xn given by the recurrence. It's either xn minus 1 plus a normally distributed random variable with mean 0, so many n's, and this is with probability alpha. I'll call it alpha n, meaning the quantity computed from the alpha value computed from this thing here. Oops. Okay, or it rejects the proposal, in which case we just stay at the same position. And this happens with probability 1 minus alpha n. Okay. Then we're going to introduce a new variable. So we're going to let a of x n be 1. No, not if, with probability. So here a of xn is a random variable, and it takes the value 1 with probability alpha n, and 0 with probability 1 minus alpha n. You can construct such a random variable using the values of alpha n and independent uniform distribution on the interval. And then what that means is that we can write the current state of our sampler like so. So it's going to be x0 plus k equals 0 to n minus 1 of a of x k, and then noting that, well, this thing is just needs to be some independent normal distribution. With this particular normal distribution, we can replace this thing by our Brownian motion. Okay. In other words, it's given by this following stochastic integral equation. Cool. Any questions about that?
Sorry, maybe I missed it, but how does n relate to b of tau n plus 1 minus b of tau n precisely? Is it just like literally equal to that?
So n is the time step?
The step to that.
Oh, right. Okay. So I guess they're identically distributed variables. So like here, n is just supposed to be some. So really, maybe it should be like n sub n, because we want to use a different random variable n at every time in iteration. And by this I mean some independent, identically distributed, with the following distribution random variables, and we might as well choose our Brownian motion in increments for that.
Sure. Sigma squared will change by time.
No, so sigma squared is the difference between. So we assume that sigma squared
depends on n, right?
We're assuming that all that because we can choose our time at tau n. So in the particular example, we're saying that they're all the same. But in general, I guess yes. If we discretize just differently, then it could. Cool. Any other questions? Great. let's move on to the next board. And now let's actually talk about these integrals. So we have the Ito and the Dratonovich. Integrals. Okay, let's write them both down. Let x and y be stochastic processes. And we define. First, I'm going to write down the definition of the Ito integral. So it is a stochastic process, which I'll call Z, which we denote like so. And it's the following limit. I had this on the board before. Here we have tk equal to k on n times t. So this was the Ito integral. So we define the Ito integral to be this, provided the limit exists. And then we also are going to talk a little bit about the Dratonovich integral, which seems to usually be denoted like this. And this is almost exactly the same formula. Except instead of evaluating x at the left endpoint of the interval from tk to tk plus 1, we evaluate it at the average. Sorry, that's not very clear. And it's times by the same integrating factor. Okay. Again, provided the limit exists. And all of these, so I should also say these are random variables, right? So this is the limit in probability rather than the almost sure limit or something else. So yeah, these things look very similar. They are actually different quantities. So if you were just talking about non-stochastic smooth functions, the choice of where you sample from in your discretized sort of short integral when you do these sums or these sort of Riemann sum type things doesn't matter. You get the same result in either case. In stochastic integration, it does matter. And we'll talk a little bit about the differences between these two in just a little. Given that we aren't really assuming a background in sort of like stochastic processes and measure theory and things like that, the conditions under which these limits exist are a little bit difficult to state. So I can write it down. I'll write down the one for the Ito integral, and we can maybe break down exactly what's going into that. They both exist under relatively general conditions, though. So the Ito exists if x and y are semi-martingales adapted to the same filtration. So let's maybe break this down. We'll break it down into two parts. So we have the semi-martingales part, and we have what it means to be, I should use a different color, and we have what it means to be adapted to the same filtration. So B is so basically what I was saying. Basically, what I was saying before about the constraints on our trading strategy C. It can't use information about so in this case, X can't use information about the future states of the stochastic process Y. The reason for doing this is you can sort of come up with, I guess, like, what's the term people use? Sort of pathological examples of stochastic processes, which look ahead at what Y is doing and force the limit to diverge. I don't think it's a big thing to worry about this condition. For A, we can break it down term by term. So first of all, a martingale. So a martingale, or rather X is a martingale if we have that X of t is equal to the conditional expectation of this. Let's call our filtration f of t. Don't need to worry too much about the details. This is true of any t and any delta t. The condition of being a martingale basically means that the average behavior of a process is in the future is predicted by its history up until this point. It's used to sort of characterize things like a fair game. So, for example, if you're playing a fair betting game, then it is the sort of the state of that game is a martingale. And we're going to relax this definition down to a semi-martingale. So a local martingale so X is a local martingale if there exists a sequence of random times, tau n, which are almost surely increasing and diverging to infinity, strictly increasing, that is, such that if we stop X at each random time, we get a martingale. So by stopping X at that time, we mean to define the stochastic process so once it gets to time tau n, it just stays at whatever X of tau n happened to be on this at that particular time. This has the effect of sort of averaging out large but rare fluctuations away from martingale behavior. So happily, all martingales are local martingales, but not all local martingales are martingales. And then a semi-martingale is, or I guess X is a semi-martingale if it is the sum of a local martingale and a process of finite variation. Which is more or less what it says, what it sounds like, and its paths are its paths are right continuous with left limits. So there's a continuity conditions on the paths of a semi-martingale. So probably don't need to worry too much about the details of these. The class of semi-martingales arose from an attempt to find the most general class of integrators for the Ito integral. And there's a reference in the notes which in some sense characterizes a semi-martingale in those terms, not exactly, but in some sense. At least it connects the definition of semi-martingale more closely to the Ito integral. It's a fairly broad class of stochastic processes, so all adapted Levy processes are semi-martingales. Brownian motion is one type of Levy process, and there's other types there's a lot of other types of Levy processes. Cool. Any quick questions on these conditions? Great. The Stratonovich integral, in general, the conditions of the existence of this thing are more difficult to sort of state in a succinct way. The definition I've given is not the most general definition of the Stratonovich integral. The reason we might want to consider it is it's the correct coordinate-independent generalization of stochastic integration. And I give a reference for that. So when you try and generalize the Ito integral to a manifold valued stochastic process, you end up with something that's coordinate dependent. And the Stratonovich integral isn't and requires less structure on the manifold. And usually you can translate between Ito integrals and Stratonovich integrals using a correction term. So there's not too much need to think to sort of favor one over the other. I'll note some sort of further reading in the notes that kind of goes into this a bit more. So there's some references there if you're interested. Cool. Let's keep cracking on. How are we doing for time? Cool. So we'll finish up by getting back to stochastic differential equations. So what we wanted to think about was equations of the following form. Oops, that's terrible. Okay, so we're going to follow some motivation given in a reference in the notes. So let eta t be noise. And what you might want is the following properties of eta. So one might want that eta t and eta s are independent. You might also want the joint distribution eta t1 plus t eta t2 plus t eta tn plus t to not depend on t. This is the property of being stationary. Basically, it doesn't sort of substantively change in statistical behavior as you look at different time periods or look at the process at different times. And you might also want that your noise is say has mean zero. Now, the conditions or the existence of such a suitable stochastic process, eta, is at least claimed in the textbook, are kind of dubious. So anything satisfying this condition and this condition can't have continuous paths. Whether that's a problem, I'm personally not sure, but it is one reason why people don't like this. Maybe a bigger problem, though, is that if also we want to control the second moment of the noise, so if we also want this, then eta t cannot be measurable in t with respect to the Borel measure on the half line. Okay, so what people do at this point is say there is a reference in the notes to sort of a generalized stochastic process. There's a reference in the notes to talking about a generalized stochastic process that does have these properties. But in practice, what most people do is the following. So instead, we think about a discrete a discretization of our time interval of every time interval, and then we can rewrite we can rewrite a discrete version of the stochastic differential equation like so. Okay, here. And this is times eta evaluated at tk times tk. And here delta tk is this. Okay. Now what we're going to do is replace our noise term times delta tk with a stationary stochastic process. So that's satisfying the condition that I had before, with independent increments and mean zero, motivated by examples from engineering or whatever sort of process they're hoping to model. People usually choose Brownian motion here. The reason for that, or the reason given for that, is it's the only such process with all of these properties which has continuous paths, although lots of Levy processes would also satisfy these properties. And their paths they're not continuous, but they're right continuous with left limits. And then we can rewrite, so once we make this substitution, we can rewrite everything like so. Sort of skipping ahead a little bit, I guess. Oops. And don't want to run out of space. And then plus this thing. Cool. And then, unfortunately, we need to jump onto the... let's just go back to 2 boards to the definition of the Ito and Stratonovich integral. And then if we take the limit as tk goes to 0, assuming all the limits exist, then this yields the stochastic integral equation, which people mean really when they write down the SDE on the first that I went through first. So that's just a normal integral. And then we have our stochastic integral. Okay, so there you have it. That's what people mean when they write down stochastic differential equations. Great. Any questions?
That's great.
Thank you.
Cool.
I guess I understand it technically why one switches from differential equations to integral equations. It's always satisfying. In terms of the analysis, integrals make functions better and derivatives make them worse. C2 function, its derivative C2, so C1. Many aspects in which integration improves things and differentiation makes it worse. But are there any deeper reasons that you're aware of why? And somehow it's sort of optional in much of analysis, but here it's like baked into the very definition that you rephrase things equations rather than actually.
Yeah. It's like it seems tough, like doing things with derivatives, because like our sort of nicest behaved stochastic process of Brownian motion is nowhere differentiable with respect to t. So thinking exactly what it means to like what is the time integral, what is the what is the time what is the rate of change of a thing that is not differentiable with respect to t? I guess it's sort of. I mean, yeah. A short answer is I don't really know. But I guess it kind of comes like probably the right way to do it is to think about like in the sort of if it's possible, the right way to do it would be to think about it in the kind of differential geometry sense of, you think about these things as path integrals, and then can you reframe that in terms of differentials in that sense. But I'm not aware of that.
Sort of suggests that even in the non-stochastic setting, integral is just better.
Yeah, maybe. I haven't looked into like non-stochastic differential equations like on manifolds, and how people think about those. So maybe that would be something to sort of, if you wanted to really think about them as derivatives.
You think about jet bundles, sections of jet bundles, and pretty well developed thing that differential equations are in a coordinate-free manner, but you don't. Well, I've thought about both of those things before, but never thought about integration. But you can define the prolongation of a function and take all its derivatives, and it's all about derivatives.
Yeah.
So you need integrals to prove that solutions exist and so on. That's a secondary. Here plays a very fundamental role.
Yeah. I'm not sure, and I don't know if it's something people haven't looked at, or if there's some good reason for it not being a productive direction. I mean, it all just seems to work so nicely with integrals, because like all of these processes like Brownian motion, etc., like all the nice processes are the limits of discrete processes, like in some sense. And like if you have a limit of discrete processes, you can just add things up and take limits, and it all sort of works. So in that sense, it kind of fits very nicely with like the most natural definitions of say like Brownian motion. Brownian motion being the limit of a random walk, and then that's the easiest way to generalize Brownian motion to a manifold. You find a way of defining a random walk on that manifold, take limits, and then if you want to do integrals, then it's all kind of easy for you. So yeah.
Cool. Thanks, Ron.
All right.
Dan, I feel like I should let you know your mic is on, I think, to text speech or something, and it sounds a bit disjointed, just in case you're going to use it later
Oh,
today.
thanks. No, yeah, that's because I'm on Discord with its threshold setting set a bit weirdly, but yeah.
Yep. That's all right. I'm back up.
All right. Cool.
See ya.
See ya.
Yeah.
Actually, I guess I'll see you in 3 weeks' time.
Yes, have fun in overseas, and good luck.
Yes, thank you. Yes, practice well.
Yeah, I'm sure it will. Good luck.